In the preceding chapters, using the formula for z and the unit normal table, you learned how to determine where a single score x is located in the distribution by converting it to a z-score. You also learned how to determine the probability for obtaining a specific score x. Now in this chapter, you're going to learn that these same things can be determined for a whole sample in relation to the distribution of all possible samples. In other words, what you have learned about the overall logic and calculations involving z will be essentially the same, but now we will focus on a sample rather than on a single score x as our focus. Perhaps this example will help clarify the idea that we can do the same things arithmetically to a distribution of means as we can do to a distribution of raw scores. The data on the left side of this slide are a distribution of x scores, which have been added up and divided by the number of scores to get the mean of the distribution. This is what we have been doing with scores ever since you learned how to calculate the mean in Chapter 3. The numbers on the right side of the slide, however, are not raw x scores, but rather are the means of 5 samples. Here we can also add the numbers, which are means themselves, divide by the number of means, and get a mean of the means. Similarly, in this chapter, we will see that we can calculate the standard deviation and eventually the z-score for a distribution of means, just like we did for a distribution of x scores in the preceding chapter. However, as you will soon see, and hopefully not be too confused by, taking many samples and getting many means will only be a theoretical idea, since in actual research we would take only one sample from the defined population. The particular sampling distribution we are interested in is called the distribution of sample means, or it's called the sampling distribution of M. Notice the difference from the term used in the previous chapter, distribution of scores, because now we are focusing on samples rather than on individual scores. Example 7.1 from the textbook is illustrated in Figure 7.1, Table 7.1, and Figure 7.2, which show what happens if we graph the means of every possible random sample from a set of data. Let's move on to the figures and table. Figure 7.1 is a frequency distribution histogram for a population of 4 scores, 2, 4, 6, and 8. For purposes of the example, we are defining these 4 scores as the whole population from which we will take samples 2 at a time. Table 7.1 shows all possible samples that could occur if we randomly sampled 2 at a time from the distribution we saw on the preceding slide. For example, in sample number 1 listed here, we randomly picked a 2 and then a 2 again. Obviously, we are sampling with replacement, since it is possible to sample 2 twice, even though there is only 1 2 in the population. Then we take the mean of our sample. We add 2 plus 2, which is 4, and then divide by 2, and we get 2 for the sample mean. Going down the rows, sample 2 gives us another possible random sample. Here we picked a 2 and a 4. Sample 3 gives us randomly picking a 2 and a 6, and so on down the line until we have the 16 samples, which gives us every possible combination of samples of 2. The means in the very last column are what we get for all those possible 16 samples. Now let's move on to show what we can do with these means in terms of distributions. Figure 7.2 is a graph of the 16 possible sample means from the preceding slide. You might want to check back just to see how they got this graph. For example, the graph is showing 3 sample means of 4. So if you go back to the previous slide, you'll see that there are the 3 means that have a value of 4. Another thing you can look at is the number of means that were 7. This graph says there were 2 of them. And if you go back to the table, you'll see that that is the case. The reason that the authors have built this figure is that we can now consider what the probability is of getting a sample mean of a certain size from this particular population. For example, we could ask the question, what's the probability of getting a sample that has a mean of 8 from that population? The graph tells us pretty easily that That would be a probability of 1/16th, because there is only one sample mean of 8 that is possible of the 16 possible combinations of samples drawn 2 at a time. This is just like in the preceding chapter, although in that chapter we were talking about the probability of individual scores in the distribution. Now we're looking at the distribution of sample means and asking the same question. What's the probability of a certain type or size of mean from a given population? At this point, we need to introduce the idea of the central limit theorem. The reason is that with realistic sample sizes, larger than the sample sizes of 2 in the preceding example, we can't actually obtain every possible sample. Just imagine, even if you have a sample size of only 10, how many possible combinations you would have of sample size 10 in a large population of scores. The mathematical concept of the central limit theorem comes to our rescue because it specifies 3 things. First, the distribution of sample means will have a mean of mu, the population mean. Second, the distribution of sample means will have a standard deviation of sigma divided by the square root of n. Sigma is just the standard deviation of the population, and n is the sample size. Third, the distribution of sample means will approach the shape of a normal distribution as n gets large. Furthermore, if either of the following conditions is met, the distribution will be almost perfectly normal. First, if the population from which the sample came is normal, the distribution will be normal. Second, if the number of scores n in the sample is relatively large, say around 30 or more, the distribution of sample means can be assumed to be normal. To be clear, what we are talking about here is a realistic research situation where we only take one sample. The central limit theorem tells us what would happen if we did take sample after sample after sample in order to get the full distribution of sample means like we did in the preceding simple example. The good news is that since we can't take all possible samples, the central limit theorem assures us that with a sufficiently large n, we can proceed as if our one sample mean came from a normal distribution of all sample means. You will learn that this concept will be very useful in inferential statistics. Figure 7.3 shows us that the standard error of the mean becomes less and less as the number of scores in the sample increases. Standard error is the measure on the vertical axis, and the number of scores in the sample is on the horizontal axis. Standard error, or sigma sub m, equals the standard deviation divided by the square root of n. As noted in the parentheses at the upper left of the slide, the standard deviation is 10. So we divide 10 by each of the square roots of sample sizes. For an example, let's look at a sample size of 4. We would divide 10 by the square root of 4 and find that the standard error is 5, which is what is shown on the vertical axis. Let's do another example for a sample size of 16. The square root of 16 is 4, and we divide 4 into 10, and we get 2.5 for the standard error, again as shown on the vertical axis. You can also see on this graph why we talk about sample sizes of at least 30 as being sufficient, because as we increase sample sizes beyond about 30, there isn't much benefit in terms of decreasing the size of the standard error. Let's recap a bit and look at the 3 different distributions that we are talking about in this section. Figure 7.4 on the next slide will clarify that we are dealing with 3 different distributions. First, the original population as a distribution. Second, the sample that we take from the population as a distribution of scores. And third, the theoretical distribution of the sample means. Here in figure 7.4a, we have the original population, in this case IQ scores. There is a mu, or mean, of 100 and a standard deviation, or sigma, of 15. Figure 7.4b shows a sample that has been taken from the population we saw in the preceding slide. The IQ scores of 25 people were randomly selected from the population. The figure is a frequency distribution showing the selected IQs. This particular sample has a mean IQ of 101.2 and a standard deviation of 11.5, which is not surprising We would very seldom get a sample that exactly represents the overall population mean of 100 and the population standard deviation of 15. Figure 7.4c is a theoretical distribution of sample means that the central limit theorem says we would get if we could pull every possible combination of samples from the population. That is, we get a normal curve with a mean of 100, just like the original population, and the standard error of the mean would be 3, at least for this particular sample size of 25. This means we're dividing 5 into the original standard deviation of 15, which gives us a standard error of the mean of 3. In summary, for this set of figures within 7.4, we are talking about 3 different distributions. It might be useful for you to keep track of that, as I know it can get confusing, especially when the graphs start looking very similar, such as Part C and Part A, even though they are different distributions. I think it would be useful to see the central limit theorem in action by looking at this demonstration from the website listed on the slide. It's fun to play with this demo, at least for stats lovers like me. You can either copy-paste or type this URL address into your web browser, or you can click on the link if you are in the slideshow view. What you see at the site is a frequency distribution of pennies in circulation organized by age, that is, by the number of years from the current year. That's why there are many pennies of a young, more recent minting and fewer from many years ago. Circulated pennies get lost, destroyed, or collected. Each time you press the Draw Samples button, a random sample from the population will be drawn and indicated by darker green bars in the upper graph showing the ages of the drawn pennies. A red arrow will indicate the mean age of the sample. In the lower graph, you will see an accumulation of your sample means, with the mean of the means also indicated by a red arrow. I recommend starting with a sample size of 60, and take samples one at a time over and over again. Type 60, or whatever sample size you choose, in the sample size box. You can also choose to take more than one sample at a time by filling in more than one in the number samples box. This speeds up creation of the distribution of sample means in the lower graph. You will find it interesting to see how the random samples jump all over the place in the upper graph, reminding us that a sample does not usually exactly represent the population. The key finding is that as you do this over and over again, the distribution of means from all the many samples begins to look like a normal distribution as predicted by the central limit theorem, and the mean of the means begins to approach the mean of the original population. Have fun! As I said at the beginning of this lesson, much of what you learned about z-scores with regard to individual scores will apply in the current chapter. We'll now begin to do that. Just as we did for individual scores, we can determine the probability of any sample and its associated mean. The formula for doing this is very similar in structure to the previous z formula. But now for sigma, we are substituting sigma with the subscript m. To get sigma sub m, we use the formula you learned earlier in this chapter of sigma sub m equals sigma over the square root of n. Once you have calculated sigma sub m, you can then put it into this z formula. Figure 7.5 is an example from the textbook that asks, if we drew a random sample of 25 students, what would be the probability of getting a sample with a mean greater than 540? The graph shows the normal distribution of SAT with mean of 500, standard deviation of 100. With that standard deviation and a sample size of 25, we end up with the sigma sub m of 20. See the boxed formula for the calculation. Then, using that sigma sub m, we next calculate the z for this sample, as shown in the other boxed formula. Notice, I drew an arrow down from the graph at 540, because that is the cutoff we are interested in with regard to finding the probability of getting a mean above 540 for a sample of 25 students. We insert the 540 into the z formula and obtain a z of 2.0. Notice again that in simple examples like this, we could have done the calculation in our head using the sigma sub m we calculated as 20. How many 20s above 500 is 540? Two of them. So we could have figured out in our heads that z, the number of standard errors of the mean above the mean, is 2.0. I want to emphasize, however, that this in the head thing is just for conceptually understanding what is going on. In almost all realistic problems, we need to use the z formula. Next, look at the arrow drawn from the 2.0 value of z to a box in the upper right corner. This box tells us that we go to the unit normal table to find out what portion under the shaded 540 tail of the graph is associated with a z-score of 2.0. We find that it is a proportion of 0.0228, or 2.28%. So we conclude that the probability in a random sample of 25 students taking the SAT test of having a mean higher than 540 is very low. It's only 0.0228. This way of talking about the probability of a certain mean size is going to be developed into inferential statistics as we move along, so be sure you understand what we just did. Figure 7.6 is an illustration of example 7.3 from your textbook. Again, asking questions about SAT scores and a sample of 25 students. This time, we are asking a slightly different question. Do you remember back in the preceding chapter how we could ask various types of questions about the tail of a distribution, or the distance from the mean, or the middle part of the distribution? Well, the same thing applies here. We can ask different types of questions, and in this one we are interested in the middle 80% of the distribution. The question is, if we take a sample of 25 students, what is their mean likely to be? We have to arbitrarily decide what we mean by likely. So for purposes of this example, we are saying the middle 80% of the distribution is likely to happen because that's around the mean of 500. So we have to determine the cutoff below the mean and above the mean for the middle 80% of the distribution. We start this time, and almost in reverse from the last example, by looking at the unit normal table at column D, as stated in the paragraph at the upper right-hand part of the slide. In column D, we look for 0.40. Why is that? It's because we want the middle 80% of the distribution. Since we are talking about normal distributions which are symmetrical, we know that 40% is on either side of the mean. Therefore, we are looking for 40%, or the proportion 0.4000 in the table, to find the z value for the cutoff point. The closest value to 0.4000 is 0.3997. Reading to the left in column A, we find that this is a z-score of 1.28. Next, we substitute into the z formula the 1.28 z-score and the given values, which are the mean and the standard deviation of the mean, as shown in the boxed formula and calculations. Notice that the z-value is entered as plus or minus 1.28. Why did I do that? The reason is that the unit normal table gives the distance from the mean cutoff, but it can be in either direction, either in a positive direction or negative. So we put it in the formula as plus or minus 1.28. I have skipped some algebraic manipulation steps in the boxed calculations, so you might want to work on these on your own to be sure you understand how I got them. If not, contact me for an explanation. We end up with m equaling 500 plus or minus 25.6. Then we add 25.6 to 500, which gives us 525.6, which is the upper cutoff as shown in the graph. Then we subtract 25.6 from 500, which gives us 474.4, which is the lower cutoff as shown in the graph. So we conclude that the middle 80% of the distribution of sample means falls between scores of 474.4 and 525.6. And the answer to the original question is that in the sample of 25 students, their average SAT score is likely to be somewhere between 474.4 and 525.6, remembering that we defined likely as the middle 80% of the distribution. We're now going to look at a couple of topics to expand on ideas already mentioned in the earlier parts of this chapter. Figure 7.7 shows that the means we could theoretically get from many samplings from a population can be all over the place. Each of the theoretical sample means is represented by a little box. As you see, about half of the sample means are going to be greater than the true population mean, about half of them will be less, and some of them will be right on target with the exact mu. Therefore, when we take a random sample, the odds are that we're going to get a sample with the mean that's not exactly the same as mu. In fact, a rare few will be quite different from the mu. As the central limit theorem tells us, if we sampled over and over and over again, we get something like this graph, approaching the shape of a normal distribution. Now, the sampling error term that you were introduced to earlier is what we're really talking about here. That is, by chance, we are going to have error in our sample mean with regard to how well it represents the population mean. The second concept that is important in this graph is the standard error of the mean, which when calculated tells us on average how spread out or how varied the theoretical set of sample means is from the true population mu. Thus, when a researcher selects a sample in order to learn something about a population, she knows that sampling error is possible, but the standard error of the mean will tell the researcher just how great that error is likely to be. This concept is a basic feature of inferential statistics. Stay tuned. In figure 7.8, we see graphically what happens as we increase sample sizes and, therefore, decrease the size of the standard error of the mean, sigma sub m. In graph A, the distribution of the means for sample sizes of 1 is pretty spread out. The samples of 1 could very likely be distant from the population mean. As we move to graph B with sample sizes of 4, we see that the theoretical distribution of the means narrows down. Finally, in graph C, with sample sizes of 100, the graph tightens up quite a bit so that we are much more likely to obtain a sample that accurately represents the larger population. In most of the chapters, the textbook authors include a section called In the Literature, so that you know how to write up the results of statistical analyses, or so that you understand how to read the results that others report. The section in this chapter talks about reporting the standard error of the mean. So far, we have been using the symbol sigma sub m. In a later chapter, when we learn how to use sample data to estimate the standard error of the mean, we will use the symbol S sub m. But in published research, the standard error of m is usually presented as capital S, capital E, capital S, capital E, capital M, or capital S, capital E, sub n. But they all mean the same thing. In this and the next slides, we'll see how this is done in table form and in graphic form. In Table 7.2 are the results of a study in which self-consciousness scores were measured in participants who were working in front of a video camera versus a control group who were not working in front of a video camera. The researchers wanted to see if self-consciousness scores were higher in one group than in the other. As we see in the mean column, the mean self-consciousness score was higher for participants who thought the video cameras were taping them. The capital S, capital E column has the standard error of the mean for each condition. The capital S, capital E values give us an idea of how the means would be spread out if we had taken every possible sample. But remember, they took only one sample. Figure 7.9 shows that we can also represent the standard error of the mean in graphic form using the so-called whiskers that come out of the blue bars whose heights represent the means of the two groups. A useful aspect of using whiskers is that they can visually give us an idea as to whether the two groups' means likely differ from one another or not. In this case, because the whiskers don't overlap, it is very likely that the difference between the means is real, not due to chance, since the likely variability of the sampling distributions of M do not overlap. In more complex research designs, we might have multiple trials or multiple conditions, as in Figure 7.10. The dots on the lines represent the mean scores on each trial for each of the two conditions, A and B. The whiskers indicate the standard error of the mean. Again, since the whiskers don't touch or overlap for the most part, we have pretty much confidence that Group A really does have higher scores than Group B on each of the trials. Another way of looking at this is we could ask if there is really a decrease in Group A or in Group B from trials 1 to 2 to 3 to 4. Well, that is a little more doubtful because their whiskers overlap a bit, but we'd have to actually apply inferential statistics to be sure about that. Visually, it has us think about that and gives us some idea of how to interpret the data, but the final word has to come from inferential statistics, not from eyeballing the graphs. Figure 7.12 is a representation of the study we've been following of newborn rats who were given a growth hormone. The question is whether the mean adult weight of the rats that get the hormone is really that different from the untreated adults' population mean of 400 grams. The graph shows that the population's mean adult weight is 400 grams with a standard error of the mean of 4. In the box to the right of the graph, I am reminding you how the standard error was calculated. In this case, the 20 standard deviation of the population divided by the square root of the sample size of 25 results in a standard error of the mean of 4. Back in Chapter 6, we learned that 95% of scores fall between z-scores of positive 1.96 and negative 1.96. In other words, 95% of all scores would be expected to be 1.96 standard deviations above or 1.96 standard deviations below the mean. The same concept can be applied to the distribution of sample means. So in this case, with the standard error of 4, we can find out what scores would be at the cutoff points of the 95% by multiplying the standard error of 4 times plus or minus 1.96. That will give us 7.84 points from the mean in either direction, which, as I've shown in the graph, are the cutoffs 392.16 to 407.84. So 95% of the sample means, if we were taking every possible sample mean, would fall between those two numbers. Here are two questions for you to think about to give you a feel for how we will discuss this in terms of hypothesis testing in the next chapter. The first question is, would a treated sample of rats with a mean of 405 be rare? Well, my answer to that would be no, because if you look at the graph, 405 falls within the 95% cutoff weights. That is, 405 is not an unusual mean in the sense that it could be due just to sampling error and not really be due to the growth hormone. The second question is, would a treated sample's mean of 410 be rare? Well, I think based on the answer I just gave, your answer should be yes, it would be rare because it falls outside the 95% region. In other words, it is an unusual event by our arbitrary definition of unusual. We don't expect to get a sample with a mean of that size very often by chance. Therefore, we would probably say that the mean of 410 is actually due to the growth hormone. It's not a guarantee that it is. We don't get absolute true answers to questions like this in science. But the probability is that the mean of 410 grams is probably due to the growth hormone, since it would be such a rare event just by chance sampling error. So there you have it. A quick summary of how hypothesis testing using inferential statistics works. As you come to better understand the ideas represented in this slide, you will have at your disposal the basic concepts underlying every one of the following chapters in the textbook. That's a broad hint that you want to be very sure you understand what's been presented so far in chapters 5 through 7 in order to be able to understand chapter 8 and beyond. I have included this last slide of demonstration 7.1 from the textbook to remind you of the basic steps involved in z-score problems, especially the first two steps of sketching the distribution with the given statistics and shading in the area of the distribution the problem is asking you to solve for.